Swayam Prabha. Digital India. Educated India.
N. Okay, and this has, yeah, and this has only resistors. Okay, this is more, less general than before. We don't have control sources and we have only resistors in this. And let's say it has two pairs of terminals. Okay, to which we can, with only resistors, if you have only that, of course all the solutions will be 0, all the currents will be 0 and voltages will be 0. We have to connect sources somewhere, and let's say we have two pairs of terminals where we can do that. Okay. And let's say I have connected V1 here. Actually, yeah, let me say I have connected VA here and VB. The sources could be anything. It could be two current sources, two voltage sources, or one voltage and one current source. Okay. I am just showing the case of two voltage sources. And you have these currents I and IB. Okay. Now, let me first make VA equal to 0. That means I will short circuit this, and in the other case I will make VB equal to 0. I will short circuit that one. Okay. Now, let me, in the first case, think of this one as the input and this IA as the result for the output. And similarly, in this case I think of VA as the input, there is only one source, right, and IB as the output. And this is a very common view, right. You have some network, you connect something here, you look at the output there. Now, what do you think is the relationship? Let's say I connect 1 volt here and I will get some IA. If I apply 1 volt here, will I be able to tell what IB is? So, please write down the Tellegen's theorem equations for this and then see what comes out. Okay. Now, you can think of these two circuits, right, and to avoid confusion, let me put hats on this. It is the same network N, but it is not the same I and IB that is flowing there, right, we do not know that. Okay. So, I have to put hats on these things. Okay. So, now I apply Tellegen's theorem to this whole circuit and then see what comes out. Please do that. If I take the voltages from this and the currents from the second circuit and form the products and add them up, that will be 0. Okay. Similarly, voltages from the second one and the currents from the first one, that will also be 0. Okay. Now, for a consistent polarity, I have to multiply VB with minus IB hat. Okay. Because I have to take the direction going in from top to bottom. Okay. So, first I will take, if I call this network N and N hat, the voltages from N and the currents from N hat. Okay. So, what is that? VB times minus IB hat plus the sum of all voltages inside this resistive network times currents in that hat currents in the corresponding hat currents in the resistive network plus the voltage across this, but that is 0. Okay. So, that I will ignore. Okay. This is over k branches inside the resistive network. Next, I will take the voltages from n hat and the currents from n. What will I get? What is the first term? V A hat times minus I A. Okay, because of the way we have defined the currents. Plus summation of V K hat I K over all branches equals 0. So far we have not used anything about it being a resistive network. So where will we use it? So V K would be, V K is the branch current times the branch resistance. Similarly, V K hat is I K hat times the branch resistance. Okay. So what will we get out of it? And I will use the resistive network part here. Okay. And similarly, in the other case, V A hat minus I A plus K V K hat I K was 0. And if I use the fact that it is a resistive network, V A hat minus I A plus K R K I K hat I K equals 0. So what do you get from these results? So clearly this part is common to the two equations, right? So this has to be equal to that one. Okay. I can of course now remove the minus signs. Now what is this? V A hat. This is the hat. Okay. Okay. Is this fine? So what is that saying about these cases? Yeah. Okay. So what is it saying about these two cases? I have a resistive network, that's all I know about it. Okay, it could have thousands of resistors, but there are two terminals exposed on this side and on that side. Okay, I apply 1 volt here, short circuit the other side. That is, I could apply voltage sources to both sides and then I set one of the voltage sources to 0. Then I measure the short circuit current, it will be something. Now if I apply 1 volt to the other side, measure the short circuit current here, what will it be? It's exactly the same, not merely proportional, it will be the same. Okay, it will of course be proportional because it's resistive network, but that's not what this is saying, right? What is the final result we got? IA by VB is IB hat by VA hat, isn't it? It's a very interesting result. If you have resistors alone, this is known as reciprocity theorem. The network is reciprocal. That is, if you apply some stimulus here, measure the effect there, and if you apply a stimulus on the other side, measure the effect here, they will be exactly the same. Okay, that is the ratio of the response to stimulus will be the same. Okay. So, please understand this theorem carefully.
We already proved reciprocity theorem when we had voltages exciting from one side or the other side. Now there could be other cases, that is, you could have current sources from either side, or voltage source from one side and current source from another side. I will not prove reciprocity theorem for all these cases, but you can follow the exact same steps as I did earlier and prove all of these as well. Okay. So just for completeness, let me take a resistive network with two ports, 1 prime and 2 prime. I have excited this side with V1, okay, and short circuited this side. I will measure the current I2, and in another case I have the same network N, of course that's very important. I excite this side with V2 hat and short circuit this side and measure I1 hat here. And reciprocity theorem says that I2 by V1 is exactly equal to I1 hat divided by V2 hat. Okay. Now let's look at the other cases. Again, a resistive network N. I excite it with a current source I1 and measure the voltage V2 here. Okay. In this case, the excitation or the cause is the current and the response or the effect is the voltage. I inject I2 hat from this side and V1 hat I obtain on the other side. And again, by reciprocity, it turns out that V2 by I1 exactly equals I2 hat by, V1 hat by I2 hat. That is, the ratio of response to excitation when port 1 is excited is exactly the same as the ratio of response to excitation when port 2 is excited. Now finally, we have the third case where again I have a resistive network N and I excite the first side, port 1, with a voltage and measure the voltage that comes out on this side, and in the other case I take the exact same network N I excite the second side with a current I2 hat and measure the current that flows in the first side. Please mind the directions of voltages and currents, otherwise you will end up with extra minus signs in different places. So reciprocity in this case says that V2 by V1, which is the response by excitation in the upper circuit, exactly equals minus I1 hat by I2 hat, which is the response by excitation in the lower circuit. Okay, we get this minus sign because of the direction of the current chosen. If we had chosen it outwards, we would have got a plus sign, but for consistency we have taken all currents as flowing inwards into the resistive port. Okay, Now we have a last case that is left, which is trivial, that is exciting the left side by a current and right side by a voltage. That is simply flipping this picture sideways, so I am not going to discuss that. Okay. Now I will show all of these things with an extremely simple circuit as an example. My resistive network is just this, has three resistors R1, R2 and R3, and let me connect first a voltage source to this side and okay, I will short circuit the second side, and in the second case I will connect a voltage source V2 hat to the right side and short circuit the left side. I will measure the current I2 in this case and I1 hat in that case. So now it's very clear that because of the short circuit, this voltage simply appears across R2. Okay, so the voltage source is connected across R2, so the current in R2 is simply V1 divided by R2. Also, because of the short circuit, no current flows in R3, and this I2 simply equals minus V1 by R2. That's because of the directions chosen. V1 by R2 is flowing from left to right, whereas I2 is taken as from right to left. Okay, so I2 equals minus V1 by R2, or I2 by V1, which is response by excitation, equals minus 1 by R2. If you now look at the lower circuit, again because of the short circuit, this voltage V2 appears across R2, and therefore the current in R2 is V2 hat by R2. And again, because of the short circuit, no current flows through R1, and because of the way we have chosen the direction of I1 hat will be equal to minus V2 hat by R2. Which means that I1 hat by V2 hat is minus 1 by R2. Minus 1 by R2. Okay. So this illustrates reciprocity. We've already proved it for the general case, but it's always a good idea to work out some real examples and convince yourselves that this is indeed the case. Now let me excite the circuit with currents instead of voltages. I'll excite it with I1 on the left side and measure the voltage V2 that's produced on the right side, and the other case I'll take the exact same network, excite it with a current on the right side and I2 hat, and see the voltage that's produced on the left side. Okay. So now what is the voltage developed here? First of all, this I1 divides into two parts. One part goes through R1, the other one goes through the series combination of R2 and R3. And by results on current division, you know that the current that flows here is I1 times R1 divided by R1 plus R2 plus R3. Okay, and V2 is nothing but this current times the resistance R3. So This is equal to V2. The response by excitation V2 by 1 will be simply R1 R3 by R1 plus R2 plus R3. Okay. Now we can evaluate V1 hat in exactly the same way. This current I2 hat gets divided into two parts, one through R3, another one through R1 plus R2. Okay. So the part of the current that flows through R2 is given by I2 hat times R3 by R3 plus R1 plus R2. This is by current division theorem.